Hello, everyone. So, the topic I would like to go through today is EMF and internal resistance. Um, we have a few formulas. If you know those formulas, you can easily understand what it is. So, if you understand the theory, if you know those basic formulas, then this is a very easy topic. So, let's just get right into it. Okay. So EMF, what is EMF? So if you think of a battery, let's say you have a battery connected in a circuit where you have a resistor. This is the battery. You know the that big vertical line is actually the positive terminal, and the other one, small one, is negative. I think we make cells like these. So if I have these symbols correct, a battery would be represented something like let's see, like two big lines and two small lines. So this is a battery. Um, Let me have the positive sign at the right spot. So yeah, so this is a battery. Normally batteries are rated, let's say, a 12-volt battery or a 24-volt battery and so on. So this, what's that? This is potential difference. We call this voltage, sometimes voltage, and sometimes PD, which is potential difference. So I'm going to tell you one thing. So EMF and potential difference, they are in a sense the same thing. So EMF, which is denoted by this symbol, and it is actually electromotive force. So remember I talked about two formulas. So I'm just going to first write those formulas. I know that you get the formulas in a formula sheet and everything, but some of the basic formulas you should always know uh, if you get a so some of the formulas you should always know even if you get a formula sheet in the exam. So you must know this formula: V is equal to IR, right? And the other formula, if you remember, that potential difference is equal to work done on a unit charge. So these are the two formulas that play the fundamental role uh, throughout this topic. So coming back to where I started from, we have a battery, right? And it says on the battery that it's 12 volts. So what is this 12 volts? That is the potential difference. So V is basically 12 volts. But EMF, which is the electromotive motive force, is not 12 volts. It must be more than that. So what is electromotive force? You know, there is a there's a resistor in the circuit, right? The circuit that you see here, there's a resistor. So a 12-volt potential difference is applied through it. So this is a resistor, and 12-volt potential difference is applied through it. Now, what is actually resistance? Resistance or resistor is basically a hindrance, or as it suggests, a resistance in the passage of electrons, or the flow of charge. So we can call this as an external resistance. So everything has some resistance. So you know batteries, how they work, they change chemical energy into electrical energy. So basically charges are moving inside the battery. So wherever charges are moving, obviously there would be some resistance. So now we have to characterize it in a way. So let's say I enclose this battery just to, make you understand that this is the battery and what is outside is a resistor. So I'm just going to call this external resistance. And usually we denote this by a capital R. And there must be an internal resistance in the battery as well, right? Because everywhere when the charges are moving, there is some resistance. So that is denoted by a small r. So yeah, just to make you understand, if you have if you are into cars like me, you would know that we often say that this car has a brake horsepower of, let's say, 240 horsepower, right? And but this car has a wheel horsepower of around 200 or 180 or 170. So what does that mean? So the engine is making 240 horsepower. So the engine is capable of making 240 horsepower, but obviously that energy has to go through gears and pulleys and also some internal parts in the engine as well. So all of that power is not coming to the wheels. So so all of that power would not come to the wheel. So what eventually come to the wheel would not be equal to 240 horsepower, right? Because that is the maximum the engine can produce. And obviously there are other mechanical bits in along the way. So maybe only 200 horsepower makes it way through the whole circuitry or through the whole mechanism and reaches the wheels. So we say that 200 horsepower is actually the wheels horsepower. So where does the other 40 horsepower go? It is consumed. It has been dissipated in the internal machinery. So the same thing happens here. If you have a battery and it gives you as an output 12 volt. So basically it is not producing 12 volts. It may be producing 14 volts or it may be producing 15 volts, and there is some internal resistance to it as well, due to which all of it does not make it outside. So if you think about it, this internal resistance and this bigger external resistance are connected in series in a way. So the total voltage or the total potential difference that the battery is producing, which in this case the brake horsepower, is actually 15 volts, but that does not make it way out of the battery because some of it is being consumed by the battery. So if I donate this EMF, which is the total voltage or potential difference that the battery makes, it's basically the sum of the voltage that makes it way out, which is V, plus I would denote the lost voltage or potential difference as small v. So this one is the rated voltage or potential difference. And this one is lost voltage or lost potential difference. So if it makes 15 volts, obviously 12 volt is coming out, then the lost voltage would be equal to 3 volts. Does that make sense? So so this is actually the concept. So EMF is what the battery can make as a total, right? And V or rated voltage or potential difference is what actually is usable outside the battery. So that is denoted by capital V. And what would be the small v? It is the lost voltage along the way. Where is it being lost? It is being lost to the internal resistance. Now, if you think about it, internal resistance is connected in series with the external resistance. So if you think about it, what happens in a series circuit? So they are connected in series, right? So what happens in a series circuit? We have the potential difference, the total potential difference being split into the components. So we have two components in a way. The total voltage is 15 volts, which is the EMF in this case. So that is total. And this capital V is what is being consumed by the external resistance because that is what is getting out of the battery. So if you know this formula, V equals IR, I can replace this V by IR because you know the current would be the same. In a series circuit, the current remains the same. So I can just write I. And the resistance of the bigger external resistance is R, which I wrote here, plus the lost voltage. So the lost voltage, where does that go? The lost voltage goes to the internal resistance, right? So that would be, obviously the current would be the same because it's a series circuit, and R is the small resistance. So this formula can be written in this form. And where does this come from? So you understand this. So you just plug in this formula for both of them, and that's what you get. So if you understand series circuit, you understand that the potential difference, the total was the EMF being distributed between the internal resistance and the external resistance, and the current would be the same for both of them because it is it's a series circuit, right? So we understand that, right? And if you have to write a definition, well, you understand now what is EMF, right? But if you have to write a definition for voltage for EMF, you always go to this formula. This formula says that voltage or potential difference is the work done on the unit charge. So in the same way, EMF can be written as the work done on a unit charge inside the battery. So the total work that is being done on a unit charge on on a unit charge is EMF. The total work done outside the battery would be this on a unit charge. But if you calculate the total work done inside plus the outside, that would be this formula. So does that make sense? So EMF is basically the sum of the rated voltage, the voltage that goes outside the battery. Like for example, the car battery. So every car has a battery because that is needed for to run some of the electronics before the car even starts, just like the starter of the car. So that battery says that it is 12 volt, but in reality it is more than 12 volt that is being made by the battery. But obviously there are internal resistance as well, so some of that is lost inside the battery. But obviously the electronics that is outside, it has a resistance, so that we need at least 12 volts to run those things. So the battery is designed in a way that uh, they design it for an EMF that can give some of its voltage, split it voltage to the internal resistance, and then eventually the voltage that comes out is 12 volt. Does that make sense? So that is the total concept of EMF. So again, EMF is actually the total voltage or the potential difference that is being produced by the battery, but some of it is being lost inside the battery, and so that is called the lost voltage, and some of it comes outside of the battery, so that is called the rated voltage or potential difference. So I'll just quickly go through an example, so that we know that we understand this completely. So if you look here, it says three identical cells, each with an EMF of 2 volt. So there are three identical cells. If you see the image on the right side, there are three identical cells. Now they're calling it cell, right? So that's why it's a good thing that I made the battery correctly, because battery is two small short lines and two long lines. So cell is denoted by, so the right symbol is one long line and one short line. So there are three identical cells, and now if you look at it, they are connected in parallel to each other. So with an EMF of 2 volts, which means, so if I have to draw it, sorry, my drawing is not that great, but I still try. I swear I'll get better any day now. Um, so yeah, so oh, they're basically connected to each other like that. So I hope I've made it right. Yeah. So This is like a universal thing. They always denote the external resistance with a capital R, and it looks like the, I don't know if they are small r, but I'm just going to assume that they are small r. And what do they say about other thing? Three identical cells, each with an EMF of 2 volts. So each of them has an EMF of 2 volt. So this is 2 volt, this is 2 volt. So that's an EMF, right? It's not the output of the battery, because output would be when it passes through this internal resistance. So this is EMF. Okay. With an internal resistance of zero point 0.2 ohms. So again, the small r is also given to us. This is zero point 0.2 ohm. This is zero point 0.2 ohm as well, because they are identical cells, and zero point 0.2 ohm as well. A current of 0.9 ampere is flowing through the circuit. So zero point 0.9 amp current is flowing through the circuit. So this is the circuit. So zero point 0.9 amp current will flow through it, which means the current that flows here is zero point 0.9 amp. Okay. Calculate the total potential difference across the cells. So what would be the total potential difference across the cells? Okay. So this is zero point 0.9. You have to calculate the total current, right? So you should know, first of all, you should know that what are the rules for series circuit and what are the rules for parallel circuit. So I can see that this is a parallel circuit, obviously, because the cells are connected in parallel. So what happens to the potential difference? So potential difference, it actually remains the same, right? So potential difference would not change. Whatever potential difference this gets from one of these circuits, it will just be that. So okay, so so first of all, let's just try to calculate the, let's say that this is a battery, this is the battery as well, this is a battery as well. So what is the voltage that we are getting out of it? What is the current that we are getting out of it? So from the first one, uh, the basically the from the first one, the current that is it is producing, because this is connected in series with this resistance, this is also connected in series with this resistance, this cell is also connected in series with this resistance. So they are all connected in series with this resistance, but obviously to each other they are connected in parallel, if that makes sense. So from the first one, the current, whatever current we get, that would be the current that goes to this resistor. Then again, this would also produce some current which will go through this resistor again, and this battery will, or this cell would also produce some resistance, some current which will also go through this battery. So whatever current is being produced here, let's say it's I. Obviously, that is connected in series, so that will go through this resistor. Again, this is an identical cell; it will also produce a similar current, and again, this battery will also produce a similar current. Now, all of them, from, because we know now they are connected in parallel to each other, right? When they combine here, they, let's call them I1, I1, and I1. When they combine all, okay, so I should have, so obviously we always say that, so this is a convention that we say that current flows from positive terminal of the cell to the negative. So the current will be flowing like this. I should have made this the other way as well. So zero point 0.9 amps is the total current, right? Uh, so this I1 plus I1 plus I1, obviously all of them are contributing so that it is getting zero point 0.9 amps. So I1 plus I1 plus I1 should be equal to zero point 0.9 amps. So that means 3I1 should be equal to zero point 0.9 amps, which gives me the current that is produced by each cell equal to 0.9 over 3, which is basically, what is that? 0.3 amps. So that is what I have got so far. So now we need to calculate the total potential difference across the cells. So we have the current now. Using this current, we can actually calculate. So we don't know the value of the resistor. If we have to use this formula, V is equal to IR. We what are the things that we already know? We know the current now. So they are connected in parallel. The current would add up at the end, but the voltage would remain the same. It won't change because they are connected in parallel. They are not connected in series. So we need to calculate what is this voltage. Hmm. To calculate this voltage, we need to know how much of this 2 volt is being consumed by this resistor. So if you remember the formula, it's so we have two formulas to actually calculate it. One could be, because we need to calculate the potential difference across the cell. One could be this formula. And what is the other formula where we have this V? So if you remember that, it was the EMF that is equal to the potential difference minus the internal resistance. Sorry, the lost voltage, basically the small v. So can we calculate the small v here? Because EMF we already know it's 2 volt, 2 volt, 2 volt. So eventually this will also so the total for all of them would be 2 volt as well because they are connected in parallel. So we already know this. So it's 2. We don't know the capital V. Uh, but we can calculate the small one because capital we can't calculate because we don't know the resistance, we don't know the total current. So yeah, we don't know the total current as actually we know the total current, but we don't know the voltage and the resistance. So there are two unknowns here, so we can't use that. So the other formula is this. We know the EMF already, which will be combined and it will still be 2 volts because they are connected in parallel. So capital B is what we need to calculate, and the small v is the lost voltage that we can calculate because we know the internal resistance that is zero point 0.2 ohm, and we know that small v would be equal to I is the same, which is not the same actually, which is I1 in this case, times the small r. So I1 is zero point 0.3 times small r is zero point 0.2. What is zero point 0.3 times zero point 0.2? That's is it 0.6? 0.06, sorry. So V is equal to zero point 0.06 ohm. Sorry, 0.06 volts. So that is the lost voltage. Obviously, the lost voltage here, lost voltage here, lost voltage here would be the same. So all of them combined will also be the same. They are connected in parallel. So it would be 2 equals V minus zero point 0.06. You can take zero point 0.06 on the other side. Have I written it correctly? Actually, I have not. It's V is equal to the total EMF minus the lost voltage. That is the formula. Uh, yeah, see, it's basically that. And V is actually equal to EMF that is 2 minus 0.06, which comes out to be so 1.94 eventually is supplied by this, by this, by this, and they combine together, and still, because they're connected in parallel, it would be the same 1.94 volts. Is that what they asked us? Yeah, not that difficult, right? So basically, there. So first is the concept that you should know. So EMF is the electromotive force, that is the total potential difference that the battery has. Obviously, it cannot provide that external to the battery because some of it will be lost inside the battery because of the internal resistance. So that's EMF. And the two formulas that you should know, one is V is equal to IR. You should know that to solve any of the EMF or internal resistance related questions. And the other formula is that EMF is equal to the potential difference, the external potential difference, plus the lost voltage or the lost potential difference inside the battery. So that's one. And you should know the rules for the series circuit. So the series circuit, the rules are uh, current remains the same throughout all the components, but the voltage gets split up among the components. And for the parallel circuit, that is the voltage or the potential difference remains the same for all the components that are connected in parallel. Uh, but the the current that adds up through all of the components, so it splits to through all of the components. So if you know all of these rules, you can solve any of the questions related to EMF or the internal resistance. I hope you like the video and you found find it useful. Thank you for watching.